Mars has been explored for decades, but the most interesting discoveries are not dramatic, hidden, or mysterious. Instead, NASA has slowly identified geological evidence, atmospheric patterns, frozen water resources, and ancient environmental clues that show how Mars has changed over billions of years. Rather than searching for fiction or conspiracy, scientists focus on soil chemistry, dust composition, crater structures, and mineral signatures that reveal how the planet once held moisture, how temperatures behave, and how seasonal dust storms reshape its surface. These scientific insights show that the real Mars story is not about sudden breakthroughs, but about patient measurements that help humanity understand a complex and evolving world. Mars features geological structures shaped by erosion, volcanic flows, ancient river systems, and deep crater basins that preserve sediment from different eras. NASA's orbiters and rovers examine canyon walls and exposed cliffs to identify minerals, such as clays, salts, and hydrated silica, which form only through long-term interaction between water and rock. This confirms that parts of Mars once had stable moisture and environments that supported gradual chemical change rather than sudden flooding. Seasonal frost deposits, extreme day-night temperature swings, and atmospheric dust patterns show that the modern climate is very active even without rain or clouds. Because vegetation never existed on Mars, wind-shaped dunes, layered sediments, and dust streaks remain preserved for millions of years without biological disturbance. These preserved patterns allow scientists to read early Martian history like a geological book, revealing how the planet once experienced flowing water, shallow lakes, and long-term climate cycles before losing most of its atmosphere and becoming cold and arid. Mars has a thin atmosphere made mostly of carbon dioxide, with only traces of nitrogen and argon. Because this atmosphere contains very little mass, it cannot trap heat, causing large temperature swings that occur even within a single day. Dust particles remain suspended for long periods, creating hazy skies and allowing storms to spread across large regions. Some dust storms can grow into global events that wrap the entire planet in a red-brown blanket for weeks, reducing surface visibility and covering solar panels with fine particles. Seasonal wind cycles move dust from one region to another, slowly shaping dunes, exposing bedrock, and redistributing sediment without the need for rain or flowing rivers. These atmospheric behaviors help scientists understand how Martian climate is dynamic even without clouds or precipitation, showing a planet that remains active through gradual wind movement and continuous dust circulation. One of the most important discoveries on Mars is the detection of large subsurface ice deposits beneath dusty plains, crater interiors, and polar regions. These ice layers are not isolated patches, but continuous sheets that extend for hundreds of kilometers, preserved beneath thin soil cover. NASA's orbiters detect these deposits using radar instruments that can penetrate the ground and measure how radio waves reflect off different material layers. Ice creates a different signal response than bedrock or sediment, allowing scientists to map its thickness, density, and lateral continuity over long distances. The presence of widespread ice has major implications for climate history because it confirms that Mars previously stored water in large, frozen reservoirs rather than losing everything to space. These ice deposits also matter for future missions because frozen water can be converted into breathable oxygen, liquid water for agriculture, and hydrogen-based fuel without transporting supplies from Earth. Understanding where ice is stable and how deep it remains buried helps researchers plan landing sites, habitat locations, and robotic extraction methods that minimize energy requirements and protect crews from radiation exposure. Radiation is one of the most challenging hazards on Mars because the thin atmosphere and lack of a global magnetic field allow energetic particles from solar activity and cosmic sources to reach the surface. These high-energy particles gradually damage equipment, degrade electronics, and increase long-term health risks for humans living outside shielded areas. NASA models show that surface shielding becomes far more effective when structures are built partially underground, allowing regolith layers to absorb a large portion of incoming radiation without requiring heavy imported materials. The Martian soil contains fine basaltic grains and dust that can be compacted or mixed with binding agents to create thick protective walls, allowing habitats to maintain stable conditions without constant energy input. Future construction concepts include robotic trenching, 3D printed regolith shelters, and modular underground tunnels that provide thermal stability as well as radiation protection. Choosing locations with deep sediment cover, predictable dust layering, and minimal erosion allows habitat design to reduce shielding mass, improve safety margins, and simplify logistics for long-duration missions. Martian dust poses a major engineering challenge because its grains are extremely fine, chemically reactive, and easily lifted by wind or electrostatic charging. These particles adhere to solar panels, mechanical joints, and airlock seals, gradually reducing power production and increasing maintenance demands. Unlike Earth dust, Martian particles can contain perchlorates and oxidizing compounds that may pose health risks if introduced into living spaces without adequate filtration. Habitat systems require layered contamination barriers, including dust-tolerant exterior joints, active airlock cleaning, and internal filtration units that capture fine aerosols before reaching occupied rooms. Robotic cleaning systems are expected to handle routine exterior dust removal to maintain solar panel efficiency and reduce manual exposure. Long-term settlement planning also considers placing critical infrastructure in partially recessed areas or protective trenches, reducing surface abrasion and shielding sensitive components from seasonal dust storms. Power generation on Mars requires more than simply installing solar panels because energy demand fluctuates with habitat activity, environmental conditions, and seasonal lighting cycles. Solar arrays experience gradual efficiency loss as dust accumulates on panel surfaces, making power output highly variable even on clear days. Storage systems must buffer these fluctuations using batteries or fuel cells that maintain consistent energy delivery when generation drops. Engineering studies show that elevated panel positioning, slight angular offsets, and automated brushing systems significantly improve long-term performance by reducing surface contamination. Habitat clusters may also rely on distributed microgrids, allowing power to be shared between modules and critical systems without overloading a single array. Redundancy planning ensures that life support, communication, and thermal regulation remain protected even if one generator or array goes offline during storms or extended low light periods. By integrating real-time monitoring, smart storage algorithms, and robotic panel maintenance, long-term settlements can stabilize energy availability without constant human intervention. Thermal regulation on Mars requires careful engineering because surface temperatures fluctuate dramatically between day and night, creating constant stress on equipment and habitat walls. Radiative heat loss into the thin atmosphere is rapid, causing surface installations to cool much faster than insulated underground structures. Subsurface environments naturally maintain more stable temperatures, reducing energy usage by minimizing heating requirements for living spaces, storage modules, and laboratory areas. Regolith layers act as a thermal mass, slowing down both heat loss and heat gain, which protects electronics, structural seals, and stored water tanks from large temperature gradients. Hybrid systems combine underground placement with active temperature control, circulating heated air or thermally conditioned fluid through internal loops. By reducing thermal swings, settlements can extend equipment lifetime, lower energy demand for climate control, and improve overall mission safety without importing heavy insulation materials from Earth. Designing a long-term settlement on Mars requires integrating geological site selection, subsurface ice access, radiation shielding, dust management, and energy stability into a single planning framework rather than treating each problem separately. Subsurface ice determines resource availability and extraction logic, while regolith thickness defines how deeply modules can be buried for radiation and thermal protection. Dust exposure influences exterior maintenance, solar array positioning, and filtration requirements at every access point. Energy systems must match settlement clustering, supporting microgrids that supply essential services even if one node is disrupted by weather or equipment degradation. Thermal regulation benefits from underground placement, reducing heating loads and extending equipment lifetime while maintaining comfortable internal conditions. By viewing the habitat as a linked environmental system instead of independent modules, mission planners can minimize construction mass, reduce operational risk, and ensure that each engineering choice simultaneously improves safety, efficiency, and long-duration habitability. The engineering concepts demonstrated on Mars illustrate how environmental conditions shape every aspect of settlement planning, from habitat shielding to thermal stability and resource extraction. Subsurface ice provides more than a water source. It becomes the foundation for life support, agriculture, and propulsion systems that reduce dependence on resupply. Dust mitigation, power stability, and underground construction are not isolated challenges but parts of a unified strategy that enables long-duration habitation without constant emergency intervention. Future missions will continue refining robotic extraction, microgrid coordination, internal recycling, and autonomous maintenance systems, gradually transforming early habitats into scalable infrastructure networks. By treating Mars as a complex environmental system rather than a simple landing site, long-term settlement becomes an engineering process rooted in geology, radiation science, thermal management, and sustainable resource use. These principles will guide exploration not only on Mars but on future missions to icy moons, deep space stations, and planetary environments across the solar system. For more space documentaries and engineering insights, explore our Orbital Atlas playlist.